We come now to the Buie-Morin power system. Thomas Buie of America and Gerard Morin of Canada both worked on developing a self-powered system which provides kilowatts of excess power to power other equipment. Thomas feels strongly that water and electricity are part of a person's rights and not a privilege which has to be paid for. They developed this self-powered generator in order to supply the electric needs of a household. First, we need to know what sort of power is used by a typical household appliances. Perhaps this illustration might help. For 10 watts you can recharge a mobile phone. Of course you don't do that all the time, only occasionally. For 30 watts or less you can power a radio set. For 50 watts you can power a fan. For 100 watts, although there are many different sizes, you can light a mains light bulb. For 150 watts or less you can power a large television set, which of course again will not be used all the time, just like light bulbs are generally not on during the daytime. 600 watts will power a refrigerator, and again that's on very seldom during the day. 1500 watts will power a kettle, and the kettle of course is only on for 5 minutes or so while it boils water. It's generally off nearly all the time, though you do need 1500 watts to be able to make it work at all. 1800 watts will power a deep fat fryer. Again, that's not used all the time. 2000 watts will power an electric fire with both electric bars on. If you have one of the electric bars switched off, then it'll only take 1000 watts. That's on a lot of the time in cold weather. You've got then 2250 watts for a typical washing machine, and that's on for a fair length of time in a day. For 2500 watts you can power a large tumble dryer. For 3000 watts to 6000 watts you can power a cooker. The load depends obviously on the number of hot plates that you have switched on and whether or not the oven is on and how warm it is. 3000 watts continuous will power a shower of hot water. 3000 watts will also power typically an air conditioning unit. These powers are only approximate, as many devices have different power settings which the user can select. For example, in Iraq during the night some households have communal air conditioning of only 1000 watts. Americans have daytime air conditioning of at least 3000 watts, while in Britain almost no households have any kind of air conditioning, while some adults in India don't even know what an electric fire is. Anyway, it would be nice to be able to power electrical equipment without having to pay for electricity, and that is what this system allows you to do, whether it is the 120 volt 60 cycles per second used in America or the 240 volt 50 cycles per second used in the rest of the world. The self-powered electricity generator, which can provide you with free electricity, is essentially very simple in outline. A battery, car battery, is used to power a standard DC to AC inverter. Then the voltage is stepped up to about 500 volts or maybe a little more. Next, a special controller is used to feed that high voltage to a powerful motor at high frequency, and finally the motor is used to spin an AC generator called an alternator, which produces the electricity which we want. Part of that electricity is fed back to the battery and inverter junction to recharge the battery and make the system self-powered. The magic which creates the extra or appears to create the extra electricity is caused by the high voltage and the high speed pulses with which that voltage is applied to a carefully chosen type of motor. With 700 watts of input power, the system puts out 10,000 watts of power. The most important components of this system are the controller and the motor. You're probably familiar with the most common types of motor, which is a single-phase motor. But the more powerful motors used in industry are three-phase motors. There are several varieties of three-phase motors, but the one which we want to use has got 36 coils around in a ring, and that comprises 3 sets of 12 windings connected in parallel, that is, across each other. This is a very powerful arrangement, as sending one pulse of current to each of these 3 chains only advances the motor by 30 degrees. So you need 12 pulses to get a full rotation. There's a continuous ring of magnets just outside the coils, and the motor which is used in this design is also found in a Samsung washing machine. A three-phase motor sounds very technical, but it really isn't. It's just a motor which has 3 sets of dry coils instead of 1. Coil set 1 is shown in red here. It's every 3rd coil. Those coils are wired in parallel, so they act as a single coil. Coil 2, marked in blue here, is another set side by side with the red set, also wired in parallel so that they act as a single coil. The 3rd coil is marked in yellow here, is a set of 12 wired all together in parallel so that they act as a single coil. So the motor effectively has just 3 coils in it, and it's made to go round by pulsing the coils in order. That is, coil number 1, then coil number 2, then coil number 3, then coil number 1 again, and so on. The more rapidly the coils are pulsed, the faster the motor rotates. And in this system, that rotation can be very fast indeed. The pulsing of those 3 coil sets, one after the other in sequence, is done by the controller unit. It's a key component in this design. The motor is a permanent magnet synchronous motor which has no sensors built into it. That sounds ever so impressive, but it's actually the cheapest type of 3-phase motor, and because it has no sensors, it is the most difficult to drive reliably. There are several varieties of 3-phase motors, but the one which we want to use has 36 coils connected in 3 sets of 12 coils in parallel. The controller consists of 2 parts. The first part is an Arduino board, which is a general purpose development board, essentially a simple computer, which can be programmed from an ordinary PC or laptop. It holds the program in its memory, and it runs whenever it's instructed to do so. The second part is an electronics link between the Arduino board and the motor. That link boosts the power fed to the motor using high-powered transistors which can feed high currents to the motor, and some other wires which feed information back from the motor to the Arduino board to give it full control of what is happening with the motor. The Arduino program powers the motor coils in sequence, and as well as that, it senses the position of the actual rotor as it spins. It does that by sensing the voltages in each of the 3 coil sets at all times. At the website here, which is www.espares.co.uk, the motor from Samsung is offered at £150 new. Also, you could get it from www.buyspares.co.uk. The genuine Samsung motor is new in both of these cases. It's not necessary for you to become an expert programmer of an Arduino board, as the program used is provided for you here. A good instruction video on how to program the Arduino Uno board is shown at this location on YouTube. The Arduino code is shown below, and it comes from simplecircuit.com. It can be downloaded directly just as a text file if you want from freeenergyinfo.com, cunningly named arduino.txt. This is the code itself. The line numbers are additional to the actual code, and it's quite a number of lines of code, but then you don't have to type these. You can just read the file, download the file, and feed it directly into your Arduino board. Right, the Arduino board looks like this. You've got a row of connectors down both sides. You have a socket which allows you to connect power to the board, and you have a socket which lets you connect your computer to the board, so that you can feed programs down into this particular Arduino board. The Arduino board drives transistors using an IR2104 8-pin dual inline integrated circuit. That's a good way of driving field effect transistor. The interface between the Arduino board and the motor needs a number of components. You need 6 IRF840 field effect transistors to actually provide the power to the motor. Those are very powerful transistors. You need 3 of those gate drivers, the IR2104 dual inline pin. You're going to need 6 33k ohm, that's 33,000 ohm, 5-watt ceramic resistors. Now, the reason why the resistors, those particular ones, have to have such a high wattage rating is because they're placed across the 400 or plus 400 power supply. The 400 volts is a nominal figure for the power supply. It might be anywhere between 400 and 500 volts. You also need 3 10k ohm resistors, also 5 watt. They're used with the 33k to drop the voltage down conveniently. You then need 6 100 ohm ordinary quarter watt resistors. They're used to feed the FET transistors. You need 3 1N 4148 diodes. They're very, very cheap and very fast. You need 3 10 microfarad capacitors. I'm showing 25 volts here. They're used in a 12 volt circuit, so in actual fact you could get away with 16 volts, but generally speaking it's better to have some fair extra voltage on your capacitors. You need 3 2.2 microfarad 25 volt capacitors, 2 push buttons to switch things on and off. One speeds the system up, one speeds the system down, slows it. You also need a 12 volt source, which could be a car battery, or it could be a bench power supply if you're already into electronics. You need a construction board of some description and some connecting wires. These components are connected up like this. We need to connect the Arduino Uno up to drive one of the 3 phases of our 3-phase motor. So to do that, we'll use an IR2104 driver chip and an IRF840 field effect transistor to feed our 400 volt power supply to the motor, and we will do that with something like 14,800 pulses per second. So the power drive for the first phase is like this. That's, for instance, your transistor IRF840. There's the grid pin, a drain pin, and a source pin. They're marked G, D, and S in the circuit diagrams. Your IR2104 integrated circuit has got pins which are numbered sequentially around it. That's the official connection inside the chip if it interests you, which it probably won't. And then you have the Arduino board. Now, 2 specific connectors on the board itself go to the IR2104. The rest of the circuit is straightforward. It's powered by 12 volts and it connects one capacitor out to line 6, which is used to feed the motor. The feed to the motor is from pins 5, 6 and 7 on the chip. 6 and 7 go to the gates of the two IRF transistors, and the central line coming from pin 6 passes through a point where one drain for the negative part of the signal is connected to the source for the transistor that handles the positive part of the signal. Those go on then to connect to phase 1 of the motor. Connecting to phase 2 of the motor is pretty much identical. There are two different connecting points to the Arduino board, and in the IR2104 circuit it's exactly the same, feeding through to the two transistors and on to phase 2 of the motor. The power drive for the third phase is the same again, but you have two different connecting points obviously to the Uno board, and the circuit is identical, feeding the positive part transistor and the negative part of the signal transistor, and they go on to phase 3 of the motor. And those three phases control the way that the motor rotates. We also need to provide feedback information to the Arduino to let it know where the motor is in its rotation. That's done by sensing the phase connections, phase 1, phase 2 and phase 3, and feeding that information into the Arduino board to the appropriate positions on the board. The voltage is very high to these phases, so what we do is we use two resistors to drop the voltage down. This arrangement, 33 to 10, drops it to about a quarter of the voltage, and that is fed directly to the Arduino board. It's also fed indirectly to the Arduino board, again using 33k resistors going through to pin AC6, alternating pin 6 on the Arduino board, and that gives you full linkage between the Arduino board and the motor. Now, a word of warning here: you can get a shock from any voltage above 30 volts. If the voltage is alternating current at a frequency under 100 cycles per second, which is as supplied by your mains wall socket, then that shock can be serious. The power described here is very easy to understand and to make, but if you get a shock from it, that shock is very likely to kill you. So this is why there is a disclaimer, and the disclaimer states quite clearly that you personally are responsible for your own actions. This document is for information purposes only, and if you decide to make or experiment with voltages higher than 12 volts, then you, and you alone, are responsible for your actions, and neither the author of this document, the web hosting service, nor anybody else is responsible for what you do or for any damage or injury caused by your own actions. Having said that, please understand that if you're careful and sensible, there's no danger in constructing this power generator in spite of the very high 400 to 500 volt input to this power driver circuit. To stay safe, you make all the necessary connections and insulate them before you apply power. So we need to construct an electronics component board to connect the Arduino to the phases of the motor. Please remember that this board will be carrying 400 volts, and so you need to enclose the board in a plastic box before powering it up. The suggestion for a physical layout for the components is based on using strip board like this. This is a rigid board which has got copper strips running along its length. These boards come in many sizes and they're very versatile. They're often referred to as Vero board, being the first manufacturer and seller of them. However, because the pin spacing of integrated circuits is just 1/10 of an inch, which is 2.5 millimeters between the holes, the solder joints can be very close together, and that does not suit a beginner to soldering. So ask a friend to help in soldering unless you're already expert. This is the circuit for the first phase, phase 1 of the motor. We want to place these components on the board, so perhaps a layout like this could be suitable. You've got your 10 microfarad capacitor, which looks large on this board layout here because the strips are so close together. The capacitor itself is not actually large. You then have your integrated circuit set to be soldered in here. You solder all of the pins, but if you didn't break the copper strip between these pins, pin 1 would be short-circuited to pin 8, pin 2 would be short-circuited to pin 7. So the red circles here indicate where you break the copper strip. So you break it in all the positions inside the connections that are made to the integrated circuit. The 0-volt line from your battery comes in here and is jumped by a wire jumper down onto this line, which feeds it to one of the pins of the second transistor. The drain and the source of these two transistors are connected to the output line from pin 6, which goes on to phase 1 of the motor. The other components are as shown on the board. The plus 12-volt line from your car battery will go to the top strip on this board. These triple breaks here are separating the 400-volt side of this board from the 12-volt side of this board. So there are breaks here on the main 12-volt supply line, so it doesn't get short-circuited in any way to the 400-volt line, and the 400-volt line itself, as soon as it hits the first transistor, is broken off the strip so that there's no chance of it getting through to the 12-volt side. These are just common sense precautions. You can make a separate board for each phase if you want, one of these for each phase, but you can put all three obviously onto a single board. Integrated circuits and transistors are very heat sensitive, so I suggest that you use a socket and solder the socket in place and let it cool down when everything is cold, and only when everything is cold then you can plug the chip into the socket. That's what an 8-pin socket looks like. You can, if you want, use this physical layout for the general arrangement. The circuit here has got two press button switches. If you press this one, the system will speed up. If you press this one, the system will go slower. The labels shown in purple here are where you connect to the Arduino board. For instance, this one here, there's a GND socket marked on the Arduino board, and the wire that comes from there goes to that particular board. These can mount on your plastic box, inside which you place this circuit board. This circuit board is a piece of that copper strip board. It has got 31 strips, and each strip has got 39 holes in it. This is the same circuit as shown on your single board. There is, in addition, of course, the 400 volt line is carried down to each of the 3 effective sections, and the 3 very large 5 watt resistors are placed on the board as well. They're connected from the motor phase 1 in this case as a divider between that and the negative line, the ground line, which goes through both to the 400 volt system and to the 12 volt system. The resistor feeding out then goes also to the Arduino. This one goes to Arduino socket 7, this one goes to the Arduino socket 6, and the same goes for each of the 3 sets of components driving the phases. So let's go back again and get our document the way up that we like to see it, because we can read the text that way. Thomas Buie describes the power supply method that he has used successfully in the past. It's a very simple arrangement which uses readily available parts which can be purchased easily through the internet. You have a car battery, which is not very expensive. You have an inverter, and that again in this case is not expensive. You have a transformer to raise that voltage up. Now that is expensive because people don't generally want to do that, so not very many of them are sold. And the transformer raises it up to 400 volts or more, and that can be rectified quite easily to give you 400 volts DC. The battery charger here looks like a cheap item, but in actual fact it isn't, because the amount of power that you want to feed back from your alternator to the battery and inverter is quite large. You're talking probably 70 amps. Now that's not chicken feed. 70 amps is a serious amount of current. Now the particular inverter that's shown here is very cheap. You can get it delivered to you in the UK for £25. That's probably about $30. I suggest that you use a European DC to AC inverter, even if you are located in the States, because that gives you a step up from 12 volts to 240 volts or so. It's somewhere in the range between 220 and 240 volts. This particular one has a power output of 2000 watts continuous or 4000 watts peak. It's cheap and it's robust, and it has to supply about 800 watts, 700 or 800 watts to the battery and the inverter itself. So we need to use something of that nature. Our problem then is the transformer to step that 240 volts up to 400 or more, 400 to 500. Getting a transformer like this is not at all easy. That's because very few people want a 400 volt power supply. The one way around that problem is to use the commonly available 115 to 220 volt transformers. That's roughly a 2:1 ratio, and it's normally used to drop 220 down to 115 or raise 115 to 220. Now the insulation on the wire should be typically 600 volts inside the transformer itself, so it should be quite safe to, instead of connecting 115 volts to the input, you connect 240 volts to the input and get probably something like 440 volts coming out. That is one way of doing it, and one supplier of transformers of that type is tester.co.uk in the UK. You will find local suppliers in your own area. You don't want to have to pay for transporting a heavy item like a transformer hundreds of miles and possibly across oceans. You might be able to get pi without a transformer if you use a voltage doubler circuit. Voltage doubler, as its name implies, doubles the voltage available. So you have a voltage, it's shown here as coming from a transformer. That transformer is inside the DC to AC inverter. So the output from the inverter goes to 2 points. It goes to one side, goes to a diode that feeds to this capacitor. It also goes to a diode in the opposite direction which feeds this capacitor. The other transformer connection goes to the common point in the middle. Now you're going to be using 400 volt capacitors here, so the 2V, or twice the voltage applied, that V is about 230 volts, so you're about 450 volts here, is coming through 2 capacitors which have a combined rating of 800 volts. That is certainly a way of increasing the voltage. I'm not sure whether or not this would work well with the power system we're describing here. I think it probably would, but the difficulty is you're only getting half wave coming out instead of full wave. If you use a transformer instead of this circuit, you'll get full wave. But another way of doing this is to use a DC power chopper. This is a circuit board which can be powered by your 12 volt battery and which can produce a wide range of outputs, including 450 volts. It's a very cheap unit. It only costs $35 from AliExpress.com. It'd probably take quite a time to be delivered to you, but that's not generally an issue. While the circuit wiring shown above is on a physical board with the electronic components attached to it, the wiring connections are normally soldered joints, but making those joints can be quite difficult because some of them are very close together. If you're experienced at soldering, then there should be no problem, but if you have not soldered before, then I recommend that you get an experienced friend to do the soldering for you. The layout is shown above on how to make the actual connection, and you need a professional level charger to deliver some 700 watts of power continuously. This particular generator system has a coefficient of performance greater than 14, but even with that high performance, it needs an input of about 700 watts for an output of 10,000 watts. Consequently, this battery charger link is very important, and commercial units which can do the job cost something like £150, which is quite different from the normal battery trickle charger, which can be got for like £20. We come now to the alternator, which produces the electrical output, which is the whole point of the system. All of the components and methods described so far have the objective of spinning the alternator indefinitely in order to provide electrical power for a household. However, please understand clearly that your local power company is most unlikely to allow you to connect your generator up to their wiring. Their wiring goes to the fuse box of your home. Consequently, it's better if you use your new supply of electrical power as if it were an emergency backup generator. That is, you connect it up to your appliances without connecting it to any external power supply or wall socket. In other words, if you want to run your washing machine, you plug your washing machine into a socket that is powered by this generator system. You do not plug it into the wall, nor do you connect your new generator to the wall socket in any way. The system described so far is perfectly capable of driving an alternator of any power level up to 10 kilowatts without altering any of the components. So the size of the alternator which you buy is up to you. Personally, I would consider an output of 5 kilowatts as being not only adequate but almost excessive, but then my electrical needs are probably far lower than yours might be. Anyway, in the UK, one supplier is Machine Mart, and they offer 3 different alternators. They look like this, and each needs to be driven at 3000 revs per minute. You have a 6.5 kVA alternator. kVA is a fancy way of saying watts, provided your power factor is 1. Most people would consider a 6.5 kVA alternator to be a 5 kilowatt unit. The pulley to go on the shaft of the alternator costs about £15. Also from the same supplier, you have a 3.5 kVA alternator. This one costs £324. This one costs £288. So for an additional £36 over the cost of this one, you get typically twice the output. They also supply us an even smaller one, which is incorrectly written down here. It's 2.2 kVA, not 22. 2.2 kVA, £240, which is not a lot less than the 6.5 kVA. So they each need, if you're going to connect them via a belt, you need a pulley wheel, one for the alternator, one for your motor, and then a drive belt. Looking at the small price difference between the alternators, there seems to be very little reason not to pick the 6.5 kVA unit, even if your expected current usage is likely to be well below that. Final step is to mount the motor unit and alternator unit together, so that the motor can drive the alternator to provide the required electrical output. It is possible to align the alternator and the motor exactly together and connect the 2 shafts pretty much directly together. That is very difficult to do, because you have to align it vertically, align it horizontally, and make sure that both shafts don't move, and then provide a flexible coupling between the 2 shafts. And the 2 shafts may well be different diameters. So I suggest that you mount the motor and put a pulley wheel on its shaft. You mount the alternator directly underneath and put a pulley wheel on its shaft, and then connect the 2 together with a drive belt, like in your car. That is a relatively easy way of connecting the alternator to the motor. And we need to thank Thomas Buie for sharing his design freely. Thomas has joined with Free Energy Special Interest Group, FESIG, and they're preparing a series of instruction videos and actual physical construction of a generator via the website truevisionofpeace.com. And you can ask questions during the live sessions. Thomas's own website is shown at this link. The Arduino code file is on this link here, and this document itself can be downloaded from this particular link here.